When we take a sequence of functions to the limit, the expectation is that the resulting function will inherit the analytical properties of its predecessors. However, as n approaches infinity, we often see a divergence in behavior. One sequence might retain its continuity, while another loses its structure entirely. Uniform convergence is the mechanism used to ensure that properties like continuity and area are preserved. This failure of preservation is most evident when we try to swap limit operations. In many cases, we find that the limit of an integral is not necessarily equal to the integral of a limit. To understand why this happens, consider a sequence of functions, fn of x, that converges point by point to a limit function f of x. This is the moving spike. For every step n, the triangle moves further to the right and grows taller, but its base narrows at the exact same rate. This ensures the area under the spike is always exactly 1. If we fix any value for x and let n increase, the spike will eventually pass that point. Once it passes, the value at x becomes 0 and stays there. Consequently, the pointwise limit of this sequence is a flat line at 0. We are left with a contradiction in the limit. The area under the final limit function is 0, yet the limit of the areas was always 1. Pointwise convergence only guarantees that individual points reach their destination. It does not provide the global control required to prevent these anomalies from escaping to infinity and breaking the calculus of the limit. To find the source of this breakdown, we have to look at the formal definition of pointwise convergence. Under the standard epsilon n logic, we defined an error margin epsilon. To prove convergence, we must find an integer n such that every function in the sequence after n stays within that error margin. The flaw in this localized definition is that the required integer n is allowed to depend on the specific coordinate x. On our moving spike graph, this means that for an x further to the right, we must wait longer for the spike to pass. We need a massive n to satisfy the margin for that point, while points to the left might have settled long ago. Because n can scale toward infinity depending on where we look on the axis, the sequence lacks a unified speed of convergence. This dependence on x means that no matter how large we choose n, there will always be points further down where the sequence hasn't settled. In the moving spike example, this tail of slow convergence is exactly where the area is concentrated, allowing the integral to remain 1 while the point-by-point values drop to 0. To preserve analytical structures during a limit interchange, we must revoke the sequence's ability to converge at different speeds. We need a rigid global boundary. Walter Rudin's definition 7.7 provides the formal solution to this lack of synchronization. The key is a quantifier swap. Now the integer n must hold true for all x simultaneously. We can no longer pick a different n for different parts of the graph. This logical change creates a physical geometric constraint, the epsilon tube. We construct this boundary by taking our limit function f of x and building a strict perimeter at f of x plus and minus epsilon. Once the sequence reaches the global integer n, the entire function is locked inside this shaded region across its entire domain. This is a much higher bar than pointwise convergence. If even a single point of the function pokes outside the tube, it is a failure of uniformity.
Uniform convergence is a rigid geometric trap that forces the entire function sequence to synchronize its approach to the limit. To prove a sequence is trapped in this tube, we use Theorem 7.9, which introduces the variable mn. Mn is defined as the supremum, or the maximum, of the absolute difference between the sequence and its limit. Geometrically, mn is simply the largest vertical distance between the approximation and the true limit found anywhere on the domain. It is the worst-case error. For uniform convergence to be valid, the limit of this worst-case error must shrink to exactly 0 as the sequence progresses. This test is powerful because it reduces the infinite complexity of a function's domain down to the behavior of a single sequence of constants. If the supremum disappears, the entire sequence is mathematically proven to be trapped within the uniform tube. Theorem 7.9 requires us to already know the limit function. If we don't, we use the Cauchy criterion in Theorem 7.8. This requires that the elements of the sequence move uniformly close to each other, rather than to a predefined limit. This logic extends to infinite sums, or series of functions, through Theorem 7.10, the Weierstrass M test.
To use the m-test, we find a constant, mn, that acts as a rigid ceiling for each individual function term across the entire domain. If the sum of these constant ceilings converges to a finite value, the underlying series of functions is forced to converge uniformly. The m-test allows us to guarantee the uniform convergence of a function series solely by evaluating a corresponding series of constant numbers. We built this precise geometric architecture for one primary reason: to safely authorize the rigorous interchange of limit operations. Theorem 7.11 is the formal proof that under uniform convergence, the order of these limits can be reversed. The proof relies on a three-part triangle inequality. Look at this first term, the distance between the limit function f of t and the sequence element fn of t. In a pointwise scenario, this term is unstable. As t changes, the error can grow arbitrarily large because the convergence speed varies across the domain. Uniform convergence fixes this. Because the entire sequence is trapped in the tube, that error term is guaranteed to remain small across the entire domain, no matter where t is placed. This uniform control ensures that the limit of a sequence of continuous functions is itself continuous. Uniform convergence repairs the broken limit, creating the bedrock necessary for rigorous calculus on infinite sequences. Pointwise convergence ensures a limit exists at every specific coordinate, but uniform convergence imposes a single global rate of approach across the entire domain. To preserve analytical properties, the approximation error must be uniformly squeezed into a vanishing tube that covers every point of the function simultaneously. These core theorems establish the conditions under which the infinite becomes predictable, allowing for the stable approximation of complex functions. Uniform convergence provides the precise control needed to move from approximations to rigorous mathematical results. If you want more deep and structured explanations from books like Rudin, including every theorem, proof idea, and example, don't forget to like, subscribe, and continue your journey into higher mathematics.